Let's now set up our kinematics object. So for this we'll have a forward kinematics object, which means I need to include that header file. And I have a typo. Now we should see what's required by the constructor of this object. The constructor here requires the track width of the robot and an update interval. So how frequently do we want to update our, do we want to perform forward kinematics? So we will have our track width. And our, let's see, I called it motor control interval. We'll call this the forward kinematics interval. And I'll somewhat arbitrarily start that out at 250 milliseconds. As for the track width, I've measured mine to be just about 17 centimeters. And that's a physical characteristic of the robot. So I'm going to start collecting those all in one place here. And in fact, they don't necessarily belong to any specific object, so I'll put those here at the top. And I'm glad I did that. That would have been a really annoying bug, not remembering to set the wheel circumference. So I'll just copy over my code from my working example here. So we have the wheel diameter. That's the measured value, the manufacturer's value, so I might as well base it off of that. And just multiply that by pi to get the circumference. I should probably scan through to see if I left any other variables uninitialized. Looks like we're good so far. For forward kinematics, let's see, I need to pass in the track width and then the interval. Now all that's left is to call setup. And going into that function, unlike our display object, setup doesn't do anything, but loop step does do something. So sort of the inverse. But you'll notice in both cases I actually do call the function, even if it doesn't do anything. The reason is I might add some functionality to the setup function later, and I don't want to forget to call it. The loop step function requires us to pass in the left and right velocities. So I'll call those left velocity and right velocity, which means I need to have those values. And to save myself from forgetting to initialize things, I'll start using this little trick. Not so much a trick as a syntax error, and I know that I won't be able to compile this without fixing and finding those values later on. So where do those come from? Well, that's something that we provide to the motor controller. So it makes sense to just grab them from the motor controller object. And now that this is starting to have a little more work, a little more code to it, I'll add a little bit of commenting and some vertical space so that the code's easier to read. Before we start working on proportional control, now would be a good time for me to introduce some new functionality that I've added to the WebSocket interface. So specifically, I've added the ability to send text over the WebSocket from this server to any clients that are connected. Specifically, I might want to do something like this. Have a string that gives the current X position, the current Y position, and the current angle, the current heading. So this would be the current pose of the object, of the robot. And it's probably also useful to pass along the current velocities of each wheel. So this is the format of the string I would like to send along. So to actually construct that string, I'm going to use the sinprintf function. For sinprintf, you pass in the string that you're going to write to, the length of that string, and then the format string. And then the dots here indicate any number of arguments that are needed to fill in the blanks that are left in the formatting string. So I need a buffer to put this into, and then this function needs to know the length of that buffer. And then I can pass in message to our sendText function. The sendText function also requires the length of the message, which is slightly different than the length of the buffer. The length of the buffer would be how many characters are you allowed to store in this message object. And out of laziness, I'll just say this is a 100 character buffer. I could technically put 100 here as the length, but the message might actually have fewer characters that are worth sending. So depending on how many characters are needed for these floats, I'll probably end up with fewer than 100 total characters that need to be sent across. There's a implicit /0 here at the end of the string, and I'd like to stop sending bytes across the WebSocket interface when I hit that /0, wherever the sinprintf function puts that /0, the null terminator. So for that reason, we'll use this string length string length function, which will actually count how many characters appear before the null terminator. All right, all that's left to do now is to actually pass in x, y, theta, VL, and VR. So I'll grab out the pose from the forward kinematics object. This is something I haven't shown you before, so you'll have to dig into the forward kinematics object to look at what this getPose object actually is. So here I'm just returning pose, and if you look at the pose object, it really is just a combination of the X position, Y position, and the current heading. So here I can say pose.x, pose.y, pose.theta, and the left velocity, and finally the right velocity. Two additional things that I'll do here to clean this up a little bit. I don't need to define this inside of my loop function. Instead, I'll define this as part of the network configuration, because that's the only place I'm going to use this message object. I will also define a new timer. The current way that this code is written is I will send text every time through this loop, which can happen thousands of times per second if I've got my code written efficiently enough. I'd really only want to send this message I don't know, every half a second or so. So let's create a new timer for that. And let's call it the message timer. And let's say it's every 500 milliseconds. To use this new object, I'll say if the message timer has fired, run this code here. Grab the pose, format the message, send the message across the WebSocket interface. Now would be a good time to upload this new program. And while this program is uploading, I'm going to show you a new web interface that I've created for this exercise. It's currently existing somewhere you can't access it, but I'll make sure to put it in a location in code that you can access before these videos get put up. So if I open this website, it should look familiar. And check, it looks like everything compiled and uploaded the new version of the program. I should now be able to, instead of sending messages from the command line here, I should be able to connect over this web browser to our example robot. And I'll need to grab the IP address and port. Paste them in here. I'll just leave the heartbeat interval at 0.8 seconds. It's set as a timeout on the robot at 1 second. We'll connect. And the nice thing about this new version of the website is it'll actually plot, assuming you're getting the same format of messages being sent across as I'm expecting, which is this format here. X equals Y equals theta equals VL and VR. As long as you format your messages that way, if I have the robot moving, we'll get new points printed here. And currently messages are being sent. Heartbeats are being sent. There are no error messages here. But the message I'm getting back from the microcontroller are a bunch of invalid numbers. I'll dig into that a bit and pause the video here. And after a bit of digging, I tracked down the error to a divide by zero here that wasn't biting me in other places. Essentially, I think the code is just reordered a little bit here such that we call motor setup and then quickly enough call kinematics.step such that a full millisecond hadn't passed. And so we were getting a divide by zero here. So I added just a small little threshold here to make sure that we were never dividing by zero. There's always some small number there that we're dividing by. And with that change, this website now works. So if I connect, and that's of course a little bit easier to see if I actually show you the robot on the screen at the same time. So unchecking the sending of heartbeats will then stop the robot's moving, the robot's motion. So the last thing I'll do here is show you what this send reset button actually does. Jumping back over to our code, if I go to the header file for WebSocket communication and look for reset, I added this reset flag. The reset flag is initialized to false, and I added these two methods. Is the reset flag set? So it just returns true if this is true, and clear the reset flag. The reset flag is only set to true inside the event callback for messages. So now we're handling heartbeat messages, and if you send a reset message, it'll set this flag to true, and that flag will remain true unless we do something about it here in our sketch. So I'll wrap up this video by showing you how to handle, and I've closed the sketch. Show you how to handle and use that reset flag. Well, certainly not the only way to do it. I'm going to propose at the top of the loop here, after we check for any messages from the WebSocket interface. If the reset flag is set, we will call a reset function, and we will clear that flag. Arguably, we could clear the reset flag whenever we check it, but I think this is a little bit more clear on what's actually happening behind the scenes. So now we just need a reset function. For now, the only thing I'll put in here is to take our kinematics object and set the pose to 0, 0, 0. Later on, we'll also reset our position controller, but this is a good place to start. Alright, so that extra bit of functionality will make it so that if I send reset, the robot will teleport back to the origin here, and then I can clear the plot and have it run the same code over and over again with my robot over on stilts. I can now use this interface a little bit more conveniently. So I've already connected, and I can start sending heartbeats. As the robot's moving, you'll see that little path start showing up, and I just have it going straight forward. Now if I stop sending heartbeats, the robot will stop. We'll stop getting things printed to the screen here. I can send a reset so that the robot thinks it's been reset at the beginning. I can clear the plot, and then I can start sending heartbeats again. And then the same code will run as if the robot were back at the origin, even if I haven't actually let it move anywhere except for to sit here on top of its kickstand. In the next video, we will take a look at how we can get this robot to go to any coordinates on the screen instead of just going straight forward or on some predefined path.